Hello there, welcome to the AP Calculus section 3.4 Homework Solutions, where we're talking about concavity and inflection points. Alright, so I'm going to bring the book into view for 1, 2, and 5. So number 1, it is concave up the entire graph. Okay, so from negative infinity to infinity, it's concave up. Number 2, so just looking at the graph, it looks like you have an inflection point about right here at x equals 1. So it would be concave up from negative infinity to 1, and then concave down from 1 to infinity. Okay, and then on number 5, it is concave up from negative infinity to negative 1, concave up, then concave down from negative 1 to 1, and then we go to concave up again from 1 to infinity. So in interval form, I went ahead and put the answers down so you can pause the video if you had trouble with any of those and look over them again. And let me know if you have any questions. So let's go ahead and do the 3 that will take the most work. Starting with number 21. So on 21 we have f of x is equal to x cubed minus 12x. So we're going to start the long process. First derivative test. So f prime of x would be 3x squared minus 12. We want to set that equal to 0. I'm going to factor out a 3 there, and we would have x squared minus 4 equal to 0. So I have critical points at x equal plus or minus 2. 2 squared is 4. That would make the parentheses negative. Negative 2 squared, also 4. I'm going to do my first derivative sign line right here. I think that's the easiest place probably to plug that in. Of course, you could factor that into x plus 2 and x minus 2 if you wanted also, but you can kind of eyeball that and see where the zeros are. So we have negative 2, positive 2. Going from negative infinity to infinity. Something less than negative 2, I'm going to put negative 10. So negative 10, if you square it, it's 100 minus 4. That's a positive. Let's plug in 0. 0 minus 4, negative 4. So that's negative. And then greater than 2 would also be positive. So we are increasing, then decreasing, and then increasing again. So we would have a minimum at 2 and a maximum at negative 2. So let's go ahead and start listing our information. We have critical points at x equals plus or minus 2. Make sure to put the x there. We have a max at the point negative 2, and then we're going to plug back into the original equation. So negative 2 cubed would be negative 8 minus 12 times negative 2. That'd be negative 8 plus 24. So that's 16. We have a minimum at 2. So that'd be 8 minus 24, negative 16. We are increasing from negative infinity to negative 2, and from 2 to infinity. We are decreasing from negative 2 to 2. All right, so we've knocked out more than half of the problem here. Now let's do the second derivative test. F double prime of x. All right, so we want to take the derivative of this, not the factored version, this, so it'd be 6x Set that equal to 0, so we have an inflection point at x equals 0. And the y value would also be 0 if you plug it back into the original equation. So our inflection point occurs at 0, 0. Let's do our second derivative sine line. I'm going to put it right next to this. I'm going to plug into 6x, negative infinity, positive infinity. Our inflection point is at 0. So if I plug in a negative 1, that'd be negative 6, so we're negative. So that's concave down. Positive 1 would be positive, so we are concave up after 0. So let's write that down. Concave down from negative infinity to 0. Concave up from 0 to infinity. Now the last step was to draw a rough sketch of the graph. So what you want to do is plot the maximum. That's negative 2 and 16. I'm going to just say that's about right there. The minimum occurs at positive 2, 16. Excuse me, positive 2, negative 16. So let's say that's about right there. We're increasing from, oops, sorry about that, it's 0, 0. Increasing from negative infinity to negative 2, but we are concave down. So something like that. We have an inflection point at 0, 0. We start decreasing from 2 to negative 2, so it's still concave down, but then we make a switch right there to more of a concave up. And then we start increasing after that. So a rough sketch of the graph. Would be something like that. Double check. We're concave up after 0. That's true. And we start increasing at 2. All right, so 2 to infinity, we start increasing. So that looks good. All right. So that's how we're going to do 23 and 31 also. We have f of x is equal to x cubed minus 6x squared plus 12x. Okay, start with the first derivative test. It's going to be 3x squared minus 12x plus 12. You could factor that and set it equal to 0. I'm going to go ahead and factor out a 3. So I'd have x squared minus 4x plus 4. Set that equal to 0. And then we can factor that trinomial. So x, and I think minus 2, minus 2. So our critical point occurs at x equals 2. So we only have one, so that's going to make this a little easier. Put a 2 there, negative infinity to positive infinity. I like to put it next to the factored version. So if I plug in a 0, I got a negative times a negative. That's a positive. If I plug in anything greater than 2, it's positive times a positive, so also positive. All right. We know at the point 2, that's not an asymptote, so we just have a flattening out of the graph at 2. So for just a singular instant there, the graph flattens out and has a slope of 0 at x equals 2. So our critical points are point x equals 2. We have no max. because those arrows don't come together, do they? And we don't have a minimum. We are increasing from negative infinity to 2, and then from 2 to infinity. And the reason that I didn't include the 2 there is because at that point, at 2, the slope of the tangent line is 0. So it's not increasing just at that point. So we have to put it in 2 different parentheses. Decreasing, never decreases. Okay, so we've got a lot of our work done. Let's do the second derivative. So we're going to take the second derivative here. That'd be 6x minus 12. Set that equal to 0. Let's go ahead and factor out a 6. So our inflection point occurs at x equals 2. So we also have an inflection point at 2, and then I've got to plug 2 into the original. So 2 cubed is 8, minus 6 times 4, 8 minus 24, that'd be negative 16, plus 24, that'd be positive 8. So we have an inflection point at 2, 8. Feel free to use your calculator there. I'm going to put our second derivative sign line right here. Put a deuce there. All right, let's plug in 0. 6 times negative 2, that'd be negative. So we are concave down. And then anything greater than 2, we're going to be positive, so concave up. So we are concave down from negative infinity to 2. Concave up from 2 to infinity. That's all the information. Now we need to have a rough sketch. We know the only point I can really plot here is the inflection point at 2, 8. So over 2, up 8. Let's say it's about right there. I know I'm always increasing. I know I'm concave down till we get to 2. So something like that. It flattens out and then concave up after that. Okay, so there you go. Something like that. Nice little curve there and flattens out right there at 2, 8. Okay, let's do 31. 31 is a trig one, so you'll want your unit circle handy. So we have f of x is equal to the sine of x over 2. I'm going to write that as 1/2 x. Same thing. So f prime of x is going to be the cosine of 1/2 x times the derivative of the block, the angle. So that's 1/2. I'm going to set that equal to 0. Our interval, by the way, on this one is between 0 and we don't include the endpoints, so it's parentheses 0 and 4 pi. All right, so you don't need to include the endpoints because you might remember from section 3.1, we don't have maxes and mins at the endpoints in an open interval. So our critical point, where is cosine 0 on the unit circle? Well, it's 0 at pi over 2 and at 3 pi over 2. Okay, so our critical points occur at pi over 2 and 3 pi over 2. Actually, that's where the 0, I'm sorry. It's going to occur at pi and 3 pi. So when you plug pi in for x, you'd have pi over 2, which cosine is 0 at pi over 2. And you plug 3 pi in for x, you'd have 3 pi over 2, also a 0 here. So we have pi and 3 pi. So negative infinity to infinity. So less than pi, I'm going to pick pi over 2. That'd be pi over 4 when we plug the pi over 2 here. Cosine of pi over 4 is root 2 over 2. That's positive. I'm going to pick 2 pi in between these two critical points. All right, so 2 pi over 2, that'd be pi. Cosine of pi is negative 1, so that'd be negative 1/2. And then we can go ahead and test anything bigger than 3 pi. Let's say, we know it's a cosine wave here, but let's say if 4 pi would be 2 pi, cosine would be positive. So we're going up, then down, and up. So we have a minimum here at 3 pi and a maximum at pi. So let's write everything down. So our critical points occur at x equals pi and 3 pi. We have a max at pi, and then the sine of pi over 2 is 1. We have a minimum at 3 pi. Plug in 3 pi here. That'd be 3 pi over 2. The sine would be of 3 pi over 2 is negative 1. We are increasing from, and it's not, I apologize so much, the end points here are 0 and 4 pi. So instead of negative infinity to positive infinity, 0 to 4 pi. Otherwise, we'd have an infinite number of critical points, right? So 0 to pi, and also again from 3 pi to 4 pi. And we're decreasing from pi to 3 pi. Okay, a little more thought has to go into this. You have to think about that unit circles. Get that out. You'll get the unit circle on the test. All right, second derivative. That's going to be, the derivative of cosine is minus sine. So it's going to be minus sine of 1/2 x times 1/2. And then you have the half out front, so it's going to be minus 1/4. So times 1/2, and then you've got the 1/2 you have to multiply that by, so negative 1/4 sine 1/2 x. Set that equal to 0. Our inflection points would occur then. Sine is 0 at pi, and again at 2 pi. Okay, so at 2 pi, that'd be 2 pi over 2, so that would be pi. So we'd have an inflection point at 2 pi. And that's going to be it, because if I put in 4 pi for x, that's an end point. So we're not going to have an inflection point there. And if we put in 0, that's also an end point. So we only have 2 pi that we have to worry about. Don't have to worry about the end points. So to the left of 2 pi, let's pick pi. Pi over 2, the sine of that is 1 times negative 1/4. That'd be negative, so we are concave down. And if we put in 3 pi, that'd be negative 1. Sine of 3 pi over 2, that'd be negative 1 times negative 1/4. That'd be positive. So our inflection point occurs at 2 pi. And when we plug in 2 pi, that'd be sine of pi, which is 0. We are concave down from, again, our endpoints, 0 to 2 pi. Concave up from 2 pi to 4 pi. So a little bit different. We don't have any infinities because they restricted our interval here, didn't they? Okay, so Hope you remember drawing all these by hand in pre-cal. I'm going to tell you that's why I had you do it. So we have 0 here. We know that we have a max at pi, so let's put pi. Have an inflection point at 2 pi. We have a minimum at 3 pi, and then our boundary, our endpoint, is 4 pi. So we have a max at pi 1 and a minimum at 3 pi negative 1. So plot that max. We have a inflection point at 2 pi 0. And we know we're concave down until we get to 2 pi. And then concave up after that. And of course the graph stops, but I just showed it going there. So there you go. I hope you remember those, and this brought back honestly, that's why I made you do for those in pre-cal who were going to take calculus. That's why I had you do this. Okay, that's it for 31. Tedious problems, I know. So let's finish up this assignment with 63 and 64. They're not nearly as much work. 63, I probably should have given you a hint on. So it says average cost. A manufacturer has determined that the total cost C of operating a factory is this cost function, where X is the number of units produced. At what level of production will the average cost per unit be minimized? The average cost per unit is C over X. So we have to get an equation for the average cost. So we know that C is 0.5x squared plus 15x plus 5,000. But we want to know the average cost, C bar. That's how you say that, C bar. If you ever take a statistics class, you will use that a lot. That's C over X. So that would be 0.5x squared plus 15x plus 5,000, all divided by X. So our equation for C bar that we're going to take the derivative, X goes into X squared. You'd have 0.5x, one of those x squared, one of the x's cancels, and then plus 15, because the x is canceled there, plus 5,000 over x, and I'm just going to save a little time here and write that as 5,000x to the minus 1. Now to find a minimum, we have to take the derivative, so that's going to be 0.5 minus 5,000 x to the minus 2. So we have to set that equal to 0. I'm going to rewrite 5,000 x to the minus 2 as 5,000 over x squared. Let's multiply both sides by x squared, and I'd have 0.5 x squared minus 5,000 equals 0. So 0.5 x squared equals 5,000. X squared equals 10,000. So the square root of 10,000, x is 100 units. Now I have to make sure that's a minimum. So to make sure it's a minimum, I'm going to do a sign line right here, because it could be a maximum. If it were a maximum, you would say, there is no minimum. So let's pick a number to the left of 100. How about 1? 0.5 minus 5,000 over 1 is going to be negative. Let's pick a million. All right, 0.5 minus 5,000 over a million squared, that's going to be a tiny, tiny number less than 0.5, so that's positive. And it is indeed a minimum. So we are good. So the answer is indeed 100 units. All right, 64 is even less intensive than this one. So on that, it says the total cost C for ordering and storing X units is this function. What order size will produce a minimum cost? We don't have to divide this one by X or anything. We have C is equal to 2X. I'm going to go ahead and rewrite this as 300,000 times X to the minus 1. So take the derivative. C prime would be 2 minus 300,000 X to the minus 2. I'm going to rewrite that and set it equal to 0. Multiply both sides by x squared, and I would have 2x squared minus 300,000 equals 0. So 2x squared equals 300,000. So x squared is equal to 150,000. So x is going to be the square root of 150,000, which is about 387 units. That's the answer. Let's check and make sure it is a minimum. All right, let's pick 1. That's less than 387, right? So 2 minus 300,000, that's negative. And let's pick a million. 2 times a million squared is going to be a lot more than 300,000, right? So it's going to be plus. So we know that it is indeed a minimum. All right. Tedious work, but it must be done. I'll talk to you next lecture.